Hello. I'd like to introduce a new abstract data type now called a priority queue. A priority queue is like a queue, like a line, except you can jump the line based on your priority. So let me define the two methods that go along with this abstract data type. The first one's push, which sounds familiar, except push takes two parameters. The first one is the priority. The second one is the object that you're trying to add. And then we have the pop method, which again takes no parameters, but it returns the object at the front of the line. Okay? And the priority is a float. So let me show you Python's implementation of a priority queue using something called a heap. So it's called Heap PQ. And we're going to make our own version of this from scratch, but I'll just show you Python's version first so we can see the ADT in action. So if I were to make, turns out, a list here, I can have the Python priority queue methods operate on this list. So if I were to say first heap push PQ, and then I said, let's say I'll put in something with priority 10 called Theo. All right. And actually, you know what? Yeah, it's really two parameters, but I'm going to put them together as a tuple to follow Python's convention here. Okay, so really just one parameter, but as a tuple. The first parameter to Python's method here is a list. We'll see that. That'll make a little more sense later. Okay, so Theo goes in with a parameter of 10, with priority of 10. Let's add Chris with priority of 20. And then let's add Celia with priority of 5. So here we had a line where Theo got in line first, then Chris got in line behind Theo, but actually Celia cut the line with a priority of 5. 5 is less than 10 or 20, so it's like when you're standing in the deli line and you pull a number. It goes in ascending order of number. So if I were now to say heap pop PQ, I would see Celia came off first. And if I did it again, I would see Theo came off next. Okay. But this is interesting. It's not like a regular queue where it's you get at the back of the line and everybody goes in order. People here can come in the line at any order. So that's the abstract data type, but then the question is, how do we implement this with a data structure? What data structure should we use? And so what I'll say is we desire a data structure that allows us to implement push and pop in big O of log and time, where n is the number of items in the priority queue. All right? So that's what we're looking for. And actually, we already know enough to do this. We could do this using an AVL tree, right? So we have done the AVL tree, and I showed you how if you maintain a balanced binary search tree, you could do additions and deletions in big O of log and time. So if I jump down to this tree here, the algorithm to find the smallest thing would be start at the root and go left, 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 left until you can't go left anymore, and that's always going to be the smallest thing. And then you could remove that, and it would only take log n time because, well, no branch is longer than log n since this is an AVL tree. And then we know it takes a constant number of rotations per node on this branch in order to fix it up. And of course, we add things and we know that was what you did in the lab. We know how to maintain the AVL there. Okay, the problem is this is very painful. This took us a long time to implement properly. And if what we're trying to do is implement the heap ADT, turns out there's a much, much simpler tree structure we can use. And so I want to introduce that now. It'll give us the same guarantees of log n, but it'll be a lot less painful. So we're going to use something called a heap. And actually, a heap is an example of storing a tree in a different format. So let me first just explain the format. This looks like a regular old binary tree. Not a binary search tree, because you see we don't have the whole left-right thing going on, with the left being less and the right being greater. But it is a binary tree. And it turns out the way you represent this tree is not with these node objects that are stitched together with pointers, but instead as a list, really. And so let me show you what I mean. I can actually unroll this whole tree by going level by level. And so I start at the root here, the first level, and that'll be the first element in my list. Then I'll go to the next level, and left to right, I'll go 8, 6. And then I'll go to the level after that, 30, 12, 9, 10. And then I'll go to the level after that, 35, 32, 20, 25, 40, 13. And so what we see here is each level ends up as a chunk in the array. So level 0 has the root, level 1 has the next 2 nodes, level 2 has the next 4 nodes, and then level 3 is going to have the next 8 nodes actually. And so interesting here, we didn't actually fill up the entire level at the bottom. We still could have put 2 more things here. There's basically 2 placeholders that we could have had that we haven't filled yet, right there. But that's how that works. Okay. Now I could have, let's say maybe I didn't have this node 25 here. Then I would store a none. Okay, it's important for me to preserve the gaps actually. I want it to be that I know exactly where to find each node in this array. So really the root should always be at index 0. The root's right child should always be at index 2, right? So 0, 1, 2 there. The left child of the root's right child should always be at index, let's see, what's that? 0, 1, 2, 3, 4, 5. Okay, so this should always be index 5. Now what we're going to have with a heap in particular here is actually a tree where we don't have any gaps up to where we are. So this is, I guess I'll call it like, we're going to have something like a left-filled balanced tree. So we're going to fill up every level except for the bottom level. But the bottom level has to be filled from the left. I can't have any gaps starting from the leftmost node in the bottom level up to the rightmost node that I have here. Okay? So it wouldn't be appropriate for me to remove this node or any of the nodes in between there. But I can stop early before I filled the whole thing up. And what that ensures is that in this representation of the tree as a list, I don't have any gaps. Okay. So that's just another way to represent a tree. And yeah, I could have gaps, but the heap is a little more specific. So it's left filled. So that's the first condition. And the second condition is that now we're going to associate numbers with each node, like I drew there. And what I'm going to say is that, so this is going to be called a min heap. You could define a max heap analogously, but I'll stick to min heap here without loss of generality. And I will say that this satisfies the property that both children of a node have a larger number than that node. Okay, so I look here and I say, okay, yep, 8 and 6, they're both bigger than 2. 30, 12, yep, they're both bigger than 8. 9 and 10, yep, they're both bigger than 6. But yes, so you see, this is a different condition from the condition that we had in a binary search tree. And in some ways, it's a little bit more flexible. Because I'm saying, okay, yeah, both children have to be bigger, but I don't really care how much bigger. I don't care whether the left one is bigger than the right one or vice versa. I just need them both to be bigger. Okay, so this is actually kind of a slightly more flexible data structure than the binary search tree in some ways, and it's going to make some algorithms a little bit easier. But I just want to show you right off the bat, we're already off to a good start, because if we wanted to find the first thing, if we thought of these as priorities, and we wanted to find the first thing that was in line, well, that's going to be at the root, right? So if it wasn't at the root, and it was the smallest item, that would be a contradiction, because I said that, both children have to be larger. So if somehow the smallest item was in the middle of the tree, let's say this was a 1 here, well, that would violate the heap property, right? Because that would be smaller than one of its parents. If it's the smallest, then it's going to be smaller than everything. So that's a contradiction. So we know that in this min heap here, the element that we're looking for to come out of the line next has to be the root. Okay. All right, so let me jump back into the Python code here. And what I've done is labeled each node here with the index that it shows up in the list. And so in my heap class, all I've got is this underlying array. So if I'm looking for a particular node, I need to know what index to go to in the array. So let me see if I can find a pattern to what the indices of the children of a particular node are. So for example, if I'm looking at this node here, then its left child is index 5 and its right child is index 6. And if you stare at this for a second, you'll realize that the pattern is, if I'm at a particular index, what I'm supposed to do is double that index, add 1 to it to get to left child, and add 2 to it to get the right child. So here I'm at index 1 in the array. 1 times 2 is 2, plus 1 is 3, plus 2 is 4. So the indices of the corresponding nodes of the left child and the right child are 3 and 4. If I go over here, I've got 2 times 2 is 4, plus 1 is 5, plus 2 is 6. Just one more example here. I got 4 times 2 is 8, plus 1 is 9, that's the left. 4 times 2 is 8, plus 2 is 10 on the right. So let me implement that in code here. So what I'm going to do here is make this method, internal method here called children. And it's going to take in the index of a node. And it's supposed to return the indices. So I'll say list of indices of children of that node. All right? So I'm going to return the indices. I'm going to think of these actually like pointers really to the nodes. So rather than returning the data in the array itself, I'm going to return pointers to the data. And so, but you know, I don't always have all my children, right? So if I ask for the children of the node at index 6 here, I wouldn't actually have any children. So let me look, I'll look at the length of the array and make sure I'm in bounds here. So I'll try to, whoops, I'll do the children first. I will try to look at the left child. So I'll say if 2 times I plus 1 is less than the length of this underlying array, then I'll append that to this list that I'm going to return. And then I'll do the same thing for the right child. If 2 times I plus 2 is less than the length, then I will add the right child here. And I will return the children. Okay? And so then the parent is actually just the floor divide of this by 2. So look, if I can see this here. If I divided this by 2, I would get I plus a half. And I round that down. Oh, actually, no, I need to tweak a little bit. It should be the floor divide. Let me do it here. It should be the floor divide of I minus 1. Okay, so I look at this here. This minus 1 is 2i divided by 2 is I. Perfect. This minus 1 is 2i plus 1. Floor divide that by 2, I get I. Okay. So this is the equation to get my parent. So that's the heap data structure overall. Now I want to pause for a second to make sure you understand this. I'll have a little exercise for you to do. And then we'll continue on and talk about how you can actually implement push and pop efficiently in this data structure.